Welcome to Lecture 14, The Sun, Part 2. As you remember from the last lecture, we finally got to the meat and potatoes of the class and started talking about what this class is ostensibly all about, which is stars and the universe. In particular, we started talking about the Sun as it represents the sort of a vanilla garden variety star in the universe, and spent some time talking about the first part of the nuclear processes that take place in the core of the Sun and make the Sun a star. We're going to continue delving into those details today, and as we enter into part 2 of our series on the Sun. Finally, as an aside, if you're wondering why I'm dressed a little bit differently than I typically am, which you're probably not, it's because it's the second time that I'm recording this lecture this evening. I did my best to get it out to you earlier this evening, but unfortunately somehow in the export process I managed to delete all of the recordings that went in with the files. And so I had to go out for a run in order to run off some of that anger before I could prepare myself to do it again. So if I come off a little too intense this time, that's the reason. Hopefully, though, we'll still manage to have some fun. So let's dig in. The Sun, Part 2. So this slide is very nearly the same as the last slide of the Sun, Part 1, which is fair enough. But just to remind you, at the bird's eye level, the nuclear reactions that take place in the Sun, for that matter, in the core of all main sequence stars, is the conversion of 4 protons into a helium nucleus, or 4 hydrogen nuclei into a helium nucleus. Of course, there are some details that go on, some of which we talked about in the last lecture, and more of which we'll talk about today. And in particular, some of those other things are involved in the conversion process of 2 of these protons into neutrons, right? Because if you look at the left, obviously we begin with 4 protons, which have 4 positive charges, and we end up with a helium nucleus, which has 2 protons, but 2 neutrons, right? So 2 of those protons are effectively converted into neutrons, and in those nuclear reactions, some other stuff happens as well. In particular, the production of 2 positrons, which are these positive white particles flying out at high speed, and these 2 neutrinos as well, represented by the Greek letter nu. It looks like a lowercase v, but it's really lowercase Greek letter nu. And finally, we have some photons flying off too, which are represented by these squiggly lines. So as I mentioned last time, the positrons are basically, and they're the antimatter particle pair to the electron, which for our purposes means they have the same mass as an electron, they have the same other properties of an electron, but the charge is reversed. And we'll say a little bit more about that today, so stay tuned for that. The neutrinos, most of the time we're going to ignore. We will come back to them, importantly, when we talk in several weeks from now about the details of stellar explosions or supernova, because in that case they actually do play an important role. But for the vast majority of the class, in fact, and certainly for the next several weeks, we'll say that they're there because for a variety of physics reasons, it's important that they're there, but they won't actually play a key role in most of our considerations. But so this is the high-level view of what's going on in the Sun, and as I said, in the core of all low-mass main sequence stars. We introduced the HR diagram a few lectures ago, and the main sequence, and we'll continue to talk about that. So there are a variety of reactions that occur in stars, and we're not going to talk about all of them in this class. We will talk about several, but the most important set of reactions we're going to talk about is what's known as the proton-proton chain. And this is a chain or a series of reactions that occur in the Sun and in the core of most, or of all low-mass main sequence stars, which is the vast majority of stars in the universe. So I told you this is the high-level view. I promised you we're going to get into a little bit more detail, and so let's go ahead and do that. So we're going to start off with the first step in the proton-proton chain, and this is something that you've already seen before because we actually introduced this in the last lecture. And it consists of fusing 2 protons, or 2 hydrogen nuclei, together to form a deuterium nucleus, also known as a deuteron, and in the meantime, in that process, emitting a positron and a neutrino as well. So this is a process that we've talked about At some length, you see it again here. We'll continue to talk about it, but this is the first step in the proton-proton chain. But now we're going to take it a step further and ask what happens after we form that deuterium nucleus. Well, it turns out that the sun is made of, wait for it, a whole lot of hydrogen. A lot of hydrogen, right? The vast majority of the star is hydrogen, and particularly when it first forms, right? As we'll talk about, and we've already mentioned, in fact, as the star ages, more and more of that hydrogen is converted to helium. And so that's going to play an important role in the evolution of the star. But for right now, we're thinking about an early stage star. It's just formed, for example. It's on the main sequence. And so the majority of of the star's stuff is still hydrogen. So if you form a deuteron, form this deuterium nucleus, it's flying around at extremely high speed in the core of a star. What is it most likely to encounter? Well, it's most likely to encounter another hydrogen. And when it does, it turns out that another nuclear reaction occurs. And in particular, this one's a pretty straightforward one. The new proton just fuses directly with the deuteron and releases some energy. So no transmutations, no conversions of protons to neutrons occur at this stage. The deuterium nucleus and proton just stick together. Because of that attraction, they release some additional energy in the process, and that comes off in the form of a gamma ray, which, just to remind you, is a very high energy photon. Remember, gamma rays are the highest energy portion of the electromagnetic spectrum. So now we're into stage 2, right? We first formed a deuteron, then that deuteron fused with another proton and formed the helium-3 nucleus. Why is it called helium-3? Well, 2 parts to that answer. First, it's helium because it has 2 protons, right? I keep coming back to this. Pull up your periodic table. Helium has 2 protons. That's what makes something helium. If something has 2 protons, it's helium. If it doesn't, it's not. Why helium-3? The 3 stands for the fact that there are 3 nucleons in the nucleus, 2 protons and a neutron. This is not, as it turns out, the most common form of helium, which happens to be helium-4. We'll see that in just a second, because that plays a very important role in the fusion in stars, but we're not quite there yet. So at this point, we formed a helium-3 nucleus out of our deuteron and our proton. So what do you think happens next? Well, you'd be forgiven if you thought that another hydrogen nucleus or another proton was at hand, because they're everywhere in the star. But it turns out we're not going to use that quite yet. Instead, what we're going to do is write down another copy of this exact set of reactions. Because, there are an absurd number of protons flying around in the sun, or any other star for that matter. And so, obviously, we start off by describing individual reactions that occur in the star. But these are happening constantly in parallel throughout the core of the sun and of every other star. And so right now I'm just going to write down another copy of the same set of reactions. So down here at the bottom, we've described that process. We have exactly the same process happening again, just a little bit away, spatially right next to our initial reaction. We've got 2 more protons flying in and fusing to form a deuterium nucleus, spits out the positron and neutrino, releases energy in the process. That deuterium nucleus flies off, then quickly encounters another proton, fuses again to form helium-3, releases a gamma ray. So every stage of this chain, every step of this path, we're constantly releasing more energy. Sometimes as gamma rays, sometimes as neutrinos, sometimes as positrons, but energy is constantly being released. So now we get to the stage where we have 2 helium-3 nuclei. And of course, when I say 2, we really have gobs and gobs of them being produced all throughout the core. But we're focusing on these 2, because these 2 now are going to encounter one another. And this is going to be an interesting reaction, where we bring these 2 helium-3 nuclei together. So 6 total nucleons, right? 4 protons and 2 neutrons. Well, it turns out that just sticking all of those nuclei together would not make a stable nucleus. But they can rearrange themselves in such a way that 4 of them stick together, 2 protons and 2 neutrons, forming a helium-4 nucleus, also known as an alpha particle. And while the two other hydrogen nuclei, or protons, fly off independently. Okay. This is important for a couple of reasons. The first is that, as we'll stress several times throughout the semester in a couple of different contexts, helium-4 is one of the most stable nuclei in the universe. And what that means for us is that if you can form a helium-4 nucleus, it's going to release a lot of energy. So I mentioned that at every stage of this proton-proton chain, energy is being released. But in this particular stage, a lot of energy is released because the helium-4 nucleus is very stable. You can think of an analogy of rolling balls down hills. And the deeper the well is, the taller the hill is, the faster the objects are moving at the bottom, the more energy is released. Same thing is happening here. These nuclei, as they form, because the helium-4 is so stable, a lot of energy is released. The second thing that I want to stress is that at the end, you see these two protons flying out into free space. And they're going to go off, and now they have the energy, and they're free to participate in yet more nuclear interactions, more nuclear reactions to power the star further. So if you go back and you look at what went into this reaction, we started at the far left of the slide with 4 protons. We added in 2 additional protons here in the middle, and so we had 6 protons total going into this, nuclear soup, if you will. At the end, what we have is a helium-4 nucleus, which is very stable, and it's going to sit around there for a while. Whereas the other 2 protons now are spit out, and they're free to go start this process over and participate in more proton-proton chain reactions. So this slide is really, if you take nothing else away from this lecture, this slide is it. So we're opening kind of with the bottom line, relatively early in this lecture. But I do recognize it's a very dense slide. Okay, so, and as I will apologize again, now that we're really in the meat and potatoes of the class, we're going to have, on a time basis or in a number of slides basis, these lectures are getting a little bit shorter in several cases. But the density of the material, I think, goes up. So feel free to pause this and stare at this slide for a while. Feel free to rewind and watch this slide again, or feel free to come back later as you need to, because there's a whole lot that's summarized right here, a lot of good stuff. I think it's interesting, and certainly it's critical for understanding how stars work. But the bottom line here is that in these 3 steps of the proton-proton chain, energy is constantly being released, and the end result is a helium nucleus and these 2 more protons that fly out to participate in yet more nuclear reactions. But there are a couple more things to say. The first is, let's come back to these positrons. So I've told you the positrons are basically positive versions of the electron. They're antimatter. And you may have heard about antimatter in the context of science fiction, but this is, and there's plenty about science fiction that's fake. This is completely legit. And what happens, what antimatter is a thing that when it encounters its particle or its matter counterpart, those things do something very technical known as annihilation, which is exactly what it sounds like. When a particle and its antiparticle meet, they disappear, they annihilate, and are converted into pure energy in the form of electromagnetic radiation. Very high energy gamma rays in this case, because rather than just converting a little bit of its mass into energy as we have occur in nuclear reactions, in the case of an annihilation, the entire mass of both particles is completely converted into electromagnetic radiation. So the electron and the positron disappear, and all you have are very high energy photons flying out. And so we've already released energy at each stage of the nuclear reactions, but now both of the positrons that were produced are going to almost immediately find electrons to annihilate with, and they will vanish as well. So if you're wondering where these electrons came from, they've been there the whole time. So we don't talk about electrons very often when we're talking about stars and fusion, because they don't participate in the fusion reactions themselves. In fact, electrons do not interact through the strong nuclear force, which is responsible for nuclear fusion. So they are produced in some processes, but not through the strong nuclear force, and so they're not going to provide any fusion energy. But if you think about how this star formed, which we haven't talked about in detail, but we will, but we have said that it forms out of clouds of interstellar gas of hydrogen. So when the stars formed, from the very beginning, for every proton, there was an electron. Now, as gravity formed this star, as it collapsed and heated up, eventually it became so hot that the atoms were unstable, the electrons were stripped off of the protons, and the star became a plasma, right? As I've said before, if you remember nothing else from this class, remember that stars are not made of gas, they're made of plasma. But having said that, those electrons are still there. They're still bound together because they're attracted electrostatically to the positive protons, and because they're gravitationally attracted on large scales. So it's a very complicated dynamical system, the star is. Lots of positive charges and negative charges flying around. Plasmas are hard to describe and hard to contain, but the electrons are there. And so in this case, that's important because once you produce a proton, or a positron rather, in almost no time it will encounter an electron, they'll annihilate, and you'll have even more energy. So energy, energy, energy. That's the bottom line here. Finally, if you're more of an equations person rather than a pictorial person, of which I have to say I run into relatively few of those in these classes, but on the off chance, it turns out that we have shorthand equations that we can use to describe this whole process as well. And so it's just a different representation of the exact same process. It's very similar to how you write down chemical reactions for those of you that have taken chemistry. And it's a three-step proton-proton chain process can be written down in the following way as shown in the upper right-hand corner of the slide now. So you have two protons which fuse to form a deuterium nucleus, excuse me, a positron and a neutrino. We then have this sort of step 1b, which is the annihilation of the positron and the electron. Note that a positron is written E+, E for electron, so it's like an electron but has a positive charge, so we write E+. E- is just an electron. Those annihilate and produce two photons. It turns out that for reasons related to conservation of momentum and energy, you can't just produce one photon when you have an annihilation. You have to produce two, and so that's how we write that. Step 2, you further fuse the deuteron or the deuterium nucleus with the proton again. You form a helium-3 nucleus and a gamma ray, and then finally in the third step of the chain, you combine through fusion again. You fuse these two helium-3 nuclei to form a helium-4 nucleus or an alpha particle, and then you spit out two protons as well. So again, if you like the equations, great. If you like the pictures, great. Feel free to spend as much time as you want staring at either one of them and pause me before going on. But I'm going to go on. So now that we understand the details, we understand exactly what's going on in the core of the star, or at least we understand what the proton-proton chain is. The next question that I want to pose is, how long can this go on for, right? Because as I mentioned a couple of times, the star starts its life as a ball of hydrogen, essentially. But as it ages, more and more of these fusion reactions occur, and more of the hydrogen is converted into helium. So how long can that process go on for? Well, it turns out the answer varies absurdly. For O-class stars, which are the hottest stars in the universe, remember surface temperatures up to 50,000 Kelvin, these stars live for around 1 million years. Now that might sound like a long time. Certainly it's longer than you or I are going to be around here for. But on astronomical timescales, this is the blink of an eye. It's extremely short-lived. On the other end of the spectrum, M-class stars, which are the smallest, lowest mass, coolest stars, can live for 500 billion years. And to put that in perspective, our best estimate for the current age of the universe is about 13.7 billion years. So this is like 30 times the age of the current universe. that an M-class star can live for. So that's sort of we keep running into mind-boggling, sort of concepts and numbers. This is yet another one. So if there were an M-class star that were formed at the beginning of the universe, not only would it still be alive today, it would still be alive, lots and lots and lots of universal lifetimes as of today in the future. So, O-class stars die out in 1 million years. M-class stars last 500,000 times longer. Okay. G-class stars, which are kind of in the middle and are relevant for us because our sun is a G-class star, they tend to live for around 10 billion years, which that's kind of a long time. It's on par with the age of the universe, a little bit less. Our star right now, our sun, has been around for about 5 billion years. And so it's about halfway through its life. So we're in no danger of seeing its demise. But it's been doing its thing for quite a while, and it's going to continue doing its thing for quite a while longer. Now, having said that, I want to step back and think a little bit about how the information I just gave you about the lifetimes of these stars impacts a stellar census. Okay, so in other words, how is the fact that O-class stars live for only 1 million years and M-class stars live for 500 billion years, and in between the stars live more or less? How is that going to impact what we see in terms of what kinds of stars are out there in the universe? And in particular, I want you to think about the following question. Groups of stars are created together in star clusters. Now, that's not a question, that's a statement. We'll talk more about that when we talk about star formation in a few weeks, but it's true. Stars don't form in isolation, they tend to form in clusters. And let's assume, and it's not a terrible assumption, that all stars form in roughly equal amounts. Okay, so in other words, imagine that you had some star cluster that formed 100 M-class stars and 100 K-class stars and 100 A-class, B-class, O-class. Every class of star got 100 stars, okay, at the beginning. And then they start burning, they start doing their thing, and time goes on. Sometime later, you come along and you look up in the star cluster and take account of what's there. What types of stars would currently, at some later time, be most abundant in our galaxy? So as usual, I'm going to pause here for 30 seconds or so. You're welcome to pause me for longer, and then I'll come back, and if you don't pause me, I'll interrupt your thoughts and tell you the answer. Okay, so if you're not ready, pause me because I'm going to spoil the surprise. Well, it turns out that there are going to be a lot more M-class stars than any other kind. And it all comes down to how quickly these things die out. If you create all sorts of stars equally, the O-class stars will die out in only 1 million years. The B-class stars will die out after a little bit more time. The A-class stars a little bit after that. And eventually, all you'll be left with are M-class stars. The point is that even if you start off with an equal population, as the population ages, the still surviving population will be skewed more and more towards the M-class end of the spectrum and away from the O-class. And it's just because the O-class stars die out so much faster. For better or for worse, this is exactly what we see. We actually mentioned this when I introduced you to the HR diagram before, and we'll revisit it a few times. But there are far more M-class stars than any other kind of star in the universe, and this is why. Once you form an M-class star, which is pretty easy to form incidentally because it doesn't take much mass, right? M-class stars are already small, and it's easier to form a small thing than it is to form a big thing. But once you do form an M-class star, it sits around forever, 500 billion years. Okay, so it's hard to get rid of those. Okay, so I want to say a word now too about another subject, which is how do we know anything about the structure of stars? Because I showed you a diagram or a schematic in the last lecture about the interior of a star, sort of the high-level structure of a star. And we're going to talk about that more here in just a second. But how on earth do we know that, right? Because it's hard to sort of dive into a star or dig into it. You can't dig into a plasma, right? So how do we know? Well, it turns out, somewhat surprisingly, at least for me when I first learned this, we know what we know about stellar interiors, at least in part, in very much the same way that we know about the Earth's interior. And if you think about it, we can dig into the Earth to some degree, but we can't dig very deep, right? It's hard to get very deep. We can dig pretty deep oil wells. It turns out we used to dig pretty big holes to put nuclear weapons down in for testing. We don't do that anymore. But what we know about the internal structure of the Earth is in many ways due to our study of earthquakes and their propagation through the materials. As the material change, the speed of the waves change. They may refract just like light refracts as it moves through different materials. And so by doing a detailed study of how seismic activity behaves as it moves through the Earth, we can actually sort of work backwards and figure out what the Earth is made of, which is pretty cool. So geology it's not, if that's the kind of geology you're doing, there's a whole lot of detailed science in there. And it turns out very similar techniques can be applied to the sun. Now, obviously, it can be a lot more difficult. And there are some significant differences. For example, the Earth is solid and the sun is a plasma. We also can't sit on top of it and put detectors everywhere in the sun. But nonetheless, solar geologists, which study something called helioseismology, have been clever enough to apply some pretty advanced techniques to effectively see inside the sun, even when they can't literally see it. So there's a whole lot of detail there. So if you're interested in that, feel free to reach out and we can certainly talk more about it. We're not going to go into any more detail about how we learn these things than that, but I wanted to throw it out there. Okay, so this is the slide that I have shown you before, but as we're going to talk in a little bit more detail in what's left of this lecture, and so I wanted to throw it back up here. Just to remind you, the main parts of the sun that we're going to talk about start with what I will very often call the surface of the sun, but the technical term for that is the photosphere. It is the surface, surface, not a physical surface, right? But it is the geometric surface beyond which we can't see. So we can see things outside the photosphere, but once you get to the photosphere, it's opaque to us. Okay, so we can't see inside the photosphere. We can only see things that leave the photosphere. So for example, if you think back to all of the work we did in talking about Boltzmann distributions and black body radiation, and how we can take an electromagnetic spectrum, take a black body spectrum, and by using Wien's law, for example, finding the peak wavelength of that spectrum, we can figure out, well, what's the temperature of that object? Well, when we do that with the sun spectrum, what we're finding is the temperature of the photosphere, because that's the surface from which that light has been emitted. And so that surface, very often, I'll say it's about 6,000 Kelvin. Here, I gave you a much more precise number, 5,778 Kelvin. And so that's what we call the surface of the sun, right? But again, obviously, it's a ball of plasma. This is not a hard surface. It's not like a baseball or a planet or anything like that. It's a geometric surface that we can't see inside. If you go inside that, the next layer is something called the convective zone. And it's not a creative name. We're going to talk quite a bit more about exactly what's going on there in the next few slides. But it's called the convective zone because convection is the dominant process in that zone. And in particular, it's the dominant process by which energy is transported from the interior of the star to the exterior of the star. If you stop and think, what's happening, what's driving everything in the star, right, are the nuclear fusion processes that are occurring in the core. Tremendous amounts of energy being liberated. Remember, E equals mc squared. Mass is being converted into free energy, And that energy is heating things up just unbelievably. That energy then starts to move out, okay? And so, but the dominant process by which that energy moves out changes as you move through the star. So in the outer layer of the star, convection is the primary means by which energy is transported. If you go a little bit closer to the core, you enter something called the radiative zone. Again, not very creative, but as you may have guessed, it means radiation, electromagnetic radiation, is the dominant mechanism of energy transport. And we'll say more about that. And then finally, in the center of the sun is a relatively small portion. I mean, it's not, it's bigger than the Earth, okay? So it's not small on that scale. But most of the sun is not the core. The core is small relative to the rest of the sun, but it's obviously a defining part of the sun in that it's the part that is hot enough and dense enough for nuclear fusion to occur. So that's where the energy is being liberated. It then travels out first through the radiative zone, then through the convective zone, finally passes the photosphere and streams in the form of electromagnetic radiation or light out into the atmosphere, first through the solar atmosphere, and then out into free space. Some of that eventually gets to us on Earth, and that's how we know it's there. So I mentioned a few ways of transporting energy, right? And we've used those ways, in fact, to define layers of the sun. So I want to back up now a little bit and finish up today's lecture by talking about the three primary methods of energy transport and what they are. Okay. So in general, there are three ways that energy can be transported from one place to another. The first of these is known as conduction. This is something you're very familiar with. When you touch a hot spoon, heat is flowing from that hot spoon into your hand through direct contact of the atoms in your hand with the atoms in the spoon. As I've mentioned, temperature is a measure of the average kinetic energy of atoms or molecules, which is a fancy way of saying how fast those atoms or molecules are going. So when a spoon is hot, that means that the atoms or molecules in that spoon are jiggling around pretty quickly. If I put my colder hand in on that spoon, I have fast jiggling atoms in the spoon bump into slower jiggling atoms in my hand, and they transmit some of that energy into my hand. Think about playing pool and hitting a fast cue ball into another ball at rest, right? You transfer a lot of that energy to the ball that you hit. Okay, so that's energy is being transferred from the hot object to the cold object through direct contact of those objects' atoms. Okay, conduction is one of the easiest methods of energy transport to understand. It's something we have a whole lot of experience with. When you hold an ice cube, it's cold because energy is flowing from you into the ice cube. You're losing that heat through conduction, and you can think of all sorts of other examples. So that's the first form of energy transport. It can happen only when things are in physical contact. Okay, so that's not how we're going to get energy from the sun, for example, because thanks be to God, we're not in physical contact with the sun. So let's move on. The second form of energy transport is radiation, which means electromagnetic radiation. This occurs when light is emitted by a hot object or a cold object, but the hotter it is, the more radiation it will emit. That light then travels through space and can be absorbed by some other object out in space, right? We've actually talked a little bit about this in the context of black bodies, right? This is exactly how black bodies work. As I mentioned, any object that isn't at absolute zero emits electromagnetic radiation. If it's relatively cold, if it's a relatively cool object, like you or me, then the radiation will be emitted almost exclusively in the infrared, and so you won't see it unless you have night vision goggles on, for example, to convert that infrared light into the visible spectrum. But if something gets hot enough, then it will have some non-trivial radiation emitted in the visible spectrum, and you'll be able to see it. For example, you see that on an electric stove. It gets hot enough to emit some in the red part of the visible spectrum. And certainly stars are the example that we think about most in this class. Those have photospheres, which are so hot that they emit well in the visible spectrum and in a variety of different colors depending upon the temperature. One crucial aspect of radiation transport is that this is the only form of energy transport that can occur in a vacuum. As you can imagine, this is going to be important for us in the context of astronomy because there's a whole heck of a lot of vacuum out there, right? Most of space is empty space vacuum. Okay, so if energy is going to be transported between a star and a planet, or between a star and a moon, or between anything that is physically separated in the universe, radiation is the way that that is going to happen. Finally, the third form of energy transport is known as convection. This one is a little bit more confusing, or so it seems in a lot of cases, but it's something that you're certainly familiar with. Essentially, it means hot stuff rises and cold stuff falls, right? You've heard this before, hot air rises and cool air falls. Certainly water, it's the same thing. If you could look inside a tea kettle as you boil water on the stove, water near the burner gets heated up. It becomes less dense as it heats. It rises. That rising pushes the cold water that's up at the top down towards the burner. As it gets down there, it begins to heat up thanks to that the flame again, or the burner, and the cycle continues. And so convection is a process through which fluid motion is induced because of temperature variations in the fluid. That fluid can be a liquid, it can be a gas, or, as in stars, it can be a plasma. So convection requires stuff, right? Again, radiation is the only sort of energy transport that can occur through vacuum, but convection is fairly large-scale currents that can exist in any sort of fluid. And in the case of a star, that fluid is a plasma. So now that you're an expert in energy transport, and that is, you can take entire classes in energy transport, and if you're interested, we can talk to the school and get them to offer a class in energy transport. I would love to teach that, but I won't subject you to any more right now. Instead, what I'll do is wrap up this lecture with this last slide. So I've talked a little bit about the structure of the sun in terms of the conduction zone, or the convection zone rather, and the radiative zone and the core. But it turns out the structure of stars depends quite a bit on how massive that star is. So the sun falls into the center category, where you have between 1/2 and 1.5 solar masses. And in that case, we've got the core in the center, and immediately outside the core is a radiative zone, where the main mechanism of energy transport is radiation. So light is streaming out from the core and going through what we'd call is a very low opacity region of the plasma. So that's a fancy way of saying it's not very opaque. It's pretty transparent to this radiation. So the radiation just streams out. Eventually, it gets to a part of the sun or part of the star where the opacity increases. And what that means is the material, the plasma, becomes more opaque to the radiation. It absorbs those photons, and when parts of the plasma begin to absorb the photons, they heat up, right? They're absorbing that energy, they're heating up. And so you're generating very hot plasma, which then rises towards the surface of the star. And you then enter the convective zone. And so you have the core at the very center. Outside of that is the radiative zone. Outside of that is the convective zone, where convection currents are the dominant mechanism by which energy is transported from the interior of the star to the exterior of the star. Remember, energy transport in a star is all about getting the huge energy and heat that's being generated in the core out to the surface, right? That's the direction of transport. The question is, what is providing that transportation? And so for a star around a solar mass between 1/2 and 1.5 solar masses, this is the structure: core, radiation zone, convective zone, and then you're out. On the other hand, if you have a larger than 1.5 solar mass star, the structure is inverted. In that case, immediately outside the core is a convective zone, where convection is the dominant mechanism of energy transport. And then outside of that, you have a radiative zone, which extends essentially to the surface of the star. So it's the processes are just inverted when the mass is greater. On the flip side, if you have a star that is less than half a solar mass, so think M-class stars, again, of which we have very many in the universe. You know, this is the most common sort of star. In that case, in fact, it's all convection. So there is no radiation zone. Convection is the dominant mechanism of energy transport throughout the star, and it's a little bit simpler. So I think I've inflicted enough pain for this time around. It's been about 40 minutes, so I don't know if I can call it short and sweet, but I appreciate you sticking with me and sticking through to the end. This has been part 2 of the sun, so we've got one more lecture on the sun, and then we'll be able to consolidate our knowledge and move on to the next set of topics. But thanks for sticking with me here, and I'll look forward to seeing you back for lecture 14.